Hello and welcome to this small video series describing some of the features in DT6 and how you might use them to analyze a real-life data scenario. My name is Tor Andreasen and I'm going to try and guide you through some of this process. When we first get our file, right, so in this case this is an old file that I opened. So I'm just going to go ahead and hit find my file, hit OK, like it as a new file, and basically you'll be brought up with our analysis panel to try and describe what it is that is going on with that machine. The first thing that we can notice is time waveform is usually where I personally like to start, so sometimes it might be on the FFT, but I like to look at the time waveform first. And when it comes to time waveforms, it's usually better to look at it in acceleration, just because it tends to give kind of a cleaner look at the signal. So now I'm going to go ahead and match it, and the first thing, let's go ahead and match this one. And the first thing that we notice is this signal right here seems to have a reasonable amount of horizontal vibration, as indicated by the large amount of red in our signal. And we also seem to have a large amount of axial relative to the others, which is a little unusual. The next thing that we notice is the vertical phase and the horizontal phase are 0 degrees apart from one another. This is usually a pretty good indication of a misalignment characteristic, regular angular misalignment, as the two shafts couple together and rotate around one another. When one of them is up, the other is up, so the two phases should be relatively equal between the two. Another thing that we notice is if we look at the other position, so over here we're looking at our motor and we're looking at the outboard side, and we notice that the horizontal is also high here, same as it was over here on the inboard side. And we notice, more importantly, these, if we zoom in, kind of like distinct spike zones, let me say. So you can see here that this one seems to be more kind of noisy and spread out throughout, whereas this one right here tends to have these kind of up and down peak impulses, which is something that is not necessarily common in good machinery, and so that's something that we should probably take a further look into. And then here we see that the vertical phase and the horizontal are about 180 degrees apart. So if they were not close to 90 degrees, we could potentially characterize this as leading towards an imbalance characteristic, but because it's closer to either 0 or 180 degrees, this would be indicating some sort of misalignment type fault scenario. And we can also, if we toggle off the vertical and horizontal, we can see, again, just as we did on the inboard side of the motor, a relatively high axial, which is not often due from imbalance, and so a misalignment scenario here would be likely a reasonable deduction from just what we have here. Then if we go ahead and just check our statistics for these guys, we can get a view of some of the values here. I personally, again, when talking about time waveform, because that's where all these values are coming from, I like to look at it in acceleration because that's closer to what the raw values themselves actually are. And we first notice that our crest factor is about give or take 2.6 here and about, let's say, 3 here. A pure sine wave is going to have a crest factor of about 1.5. So these crest factors are a little bit higher, and what that means is that the ratio of the peak to the RMS is greater than it should be for a pure sine wave, which is often indicating either misalignment characteristics or large impacts or resonance characteristics, because it means that at some point there's a peak that's higher than the majority of the energy of the signal, and so you would get a higher crest factor. Another thing to note is the kurtosis value is not reasonably high, so there's not a huge amount of information we can deduce from those two. But if we go ahead and let's go back to the time waveform, but let's look at the pump side. So if we scale it to the bottom one, then we have these two scales as the same right now, same units and everything. And we notice that the outboard side has an incredibly small vibration relative to this one. So if we just zoom in, we can kind of roughly compare the scales. And here, let's say the peak amplitude is, let's say about 0.1 Gs. But then over here, our peak amplitude is closer to, either 1 G or 1.25 Gs, kind of over here. So there's a factor of almost 10 difference between this one this one. So just based on that, it would be a reasonable assumption to say that whatever is causing the vibration, the source of that vibration, i.e. the thing causing the energy of the vibration in the first place, is probably on the motor side. So we can get a rough idea that the thing causing the majority of the vibrations is actually in the motor itself and not actually in the pump side. And so that most of what we would be seeing on the pump side is going to be leakage from whatever fault is on the motor side. So if we go ahead and zoom in on the pump, and I'll go ahead and bring up the pump inboard here and the outboard here, the first thing that we can see is, again, really large axial vibrations relative to the vertical and horizontal. It's a pretty good indication of a misalignment type characteristic. But over here we kind of see that the vertical and horizontal phase, again here, are closer to 90 degrees. So this would indicate that these two, as far as the pump side go, are more characteristic of imbalance characteristics as opposed to misalignment ones. So it's a little bit of a contrast from what we had before, but it could potentially be a slightly different scenario going on. But the other thing that we notice is if we zoom in, let's say here, again, we see kind of these big, like right here is a good one. We see a big spike, and then if we turn it off, we see kind of a big spike, and then it kind of rings down. And if I increase my frequency range over here, just clicking this frequency, and bring it up to, let's say, 1600 hertz, which for those of you who work on RPM is 96,000 RPM, and we zoom back out again, we can definitely see a relatively unusually high axial vibration, and we see this really big and distinct horizontal vibration, right? And when we're going through and looking at that, we can still see some of these spikes, and if we even go as far to look at it as the horizontal, we still see kind of what looks like spikes that are ringing down. And spikes are a pretty good indication of impacts. And so what causes impacts? Well, impacts are things where basically two pieces of metal or two objects come into contact and they basically smash into one another, and the amount of force that gets applied gets amplified from the impact itself, and then due to inherent losses it'll kind of ring down in vibration, the same way that if you strike a tuning fork, the tone will eventually die off, but it'll kind of ring back and forth at a very specific frequency. So that kind of shows in the time waveform what it is that we are, based on just looking at this, kind of what characteristics our fault has. And if we go to the statistics on the pump side, we see crest factors that are a lot bigger. I mean, like right here, 4.81, right? That's, now we're getting up there. There's some journalistic paper type evidence that would argue that crest factors of 4.5, 5, 5.5, 6, and up are pretty good indications of impact type faults, but also like specifically related to bearing faults usually, as opposed to gear faults. So the pump itself seems to be getting a lot of impacts associated with it that ring down over time, because we have a relatively high crest factor as a relationship, which means that there's peaks that go out further relative to where the majority of the signal is. So if the majority of the signal you can count as kind of if we just look at the horizontal, for instance, it's just the middle red shading. Well, these peaks go well further away than where kind of the majority of the red is. So that's kind of indicating that you have these peaks of an impact where it spikes in vibration for a split second and then dies off, and then it spikes again and then it dies off. So that talks a little bit about what it is that and how you could use the time waveform specifically to talk about and analyze what it is that the vibration might be doing. And in the next part, we're going to talk about kind of what the FFT tells us, specifically related to looking to see if what inherent problems might be underlying. Because as of right now, our biggest vibrations are over here on the motor side, and now that we brought the filter out, we can see we got impacts all the way up to 10 Gs, which are really big acceleration impacts. The only thing that would be really causing this much acceleration is something that's impacting, because when it impacts, you get these really big spikes in energy. So, a majority of signals are going to be really small acceleration, but since we have close to 10 Gs on the horizontal, it's not a faulty assumption to say that this is probably some sort of either a resonant characteristic or a bearing impact. And in the next part, we're going to look at the FFT to see if we can further eliminate down what it is that's causing this enormous vibration. Because right now it kind of looks like, if you look at the motor side, it kind of looks like a misalignment characteristic. But if you look at the pump side, it kind of looks like an imbalance characteristic. But everything has really big vibration. It's got spikes. The crest factors seem to indicate, at least on the pump side, that there's some sort of large impact force going on that's creating a relatively high crest factor. And the FFT is hopefully going to be able to clear up some of the confusion and give us a few more answers and insight into what the inherent issues are here. Hi, welcome back. In this part of this video, we're going to talk about the same file that we were looking at before, and instead of looking at it in the time waveform and just based on pure statistics numbers, kind of what you would get like from a trending sort of scenario, we're going to look specifically at what sorts of characteristics are in this file that would be present in the FFT so that we can try and better eliminate out what faults might be present. And if we go to the FFT, here we have the inboard side on the top, and here we have the outboard side of the motor on the top. We're going to go ahead and auto scale it, and let's auto scale this too. Then we shall match it to the bottom. And the first thing we notice is that if we zoom out, now that we're looking at the full scale range, there's these really high vibrations at 40,000 CPM, 45,000 CPM, 50,000 CPM, and so on. And we also see these high vibrations up here on the inboard side. So the first thing we might do is say, okay, well, that seems a little weird, so let's go ahead and zoom in on those and take a look at it. We'll go ahead and bring that up. We'll match to the top one. And we'll match. So now we have the same scale on both sides. If we look at it, we can see that we're in a relatively high frequency range right now, but once you get into higher frequencies, and where the cutoff is kind of arbitrary, but I like to look at things in acceleration. Since it's an accelerometer, it's going to best measure things in acceleration because it's not going to have to add any errors from the integration portion of it. And we see, look here, this frequency right here is close to 2 Gs, right? It's quite large, and we seem to have what appears to be equally spacing parts. So the first thing we might do is say, okay, well, I wonder if these are somehow related to one another. So what we do is we might bring up the sideband cursor right here, and we'll put this sideband cursor just on the largest peak. Now, in real life, what the center frequency is does not necessarily have to be the largest frequency, but for most of the time, the middle frequency is going to be the largest one. Then we'll just go ahead and bring these sideband cursors down until they seem to match there. Look at that. They match almost identically. So if we turn them off, we can see here they are. And we put it back on, and they match up exactly. And that frequency is just about 5,520 CPM. So what does that tell us? Well, that tells us that these frequencies are likely related to one another by a frequency that's at 5,520. So the first thing you might ask is, well, are those harmonics of something? So if we turn off those sidebands and we go over down low and we look at our machine, well, I know from my own experience that this machine was running at 15 Hertz, is this little peak right here. And so I'm going to go ahead and zoom in on that guy, and then I'll go ahead and try and select it right here. So we'll put it at 15, and you can see that. And then we'll zoom back out. Let's match the bottom one. So we're in the same spot again now. Actually, let's go back. Now that we have that cursor on here, we can add harmonics of it to try and see if they're harmonics of the fundamental frequency, because they might be. There's no guarantee they're not. But if we look up high, only this one gets close to matching, but it doesn't technically match. And if we're looking at RPM, that frequency is close to 43,650 is where the harmonic is. In this case, the 47th harmonic, but our peak is at 43,600. So it's not necessarily a harmonic, because if it was, it should be lining up identically, and more importantly, we have a bunch up here that don't line up on the harmonics exactly. If it was true harmonics, they should be lining up all the way through. So what might be happening here? Well, if we turn on our sidebands again, we see that our cursor width spacing is about 5400. And so now let's say we were looking at this side and we turn on its sidebands, and just for the sake of argument, we'll bring it to its center at the biggest peak, and then we'll bring this guy down and see if we can match anything. But if we go ahead and type in the exact same number, and we really line this guy up right, let's put it right there, well then we can see that it lines up pretty well with all the other peaks. And that's a pretty good indication that because the spacing here is the same spacing as it is here, those are likely sidebands of some sort of underlying bearing fault. But the interesting part is that if we look straight up, because we have the same scale, so we can look straight up on the graph and see if it matches, the big peak up here, right there, actually matches not with this big peak, but with this one right here. And this big peak actually matches with this one up here. And that is likely to tell us that these aren't actually the same problem. Because when we're looking at bearings, we have these frequencies high up that are equally spaced, and as they should be. And what we know about bearing faults is that when bearings have failures, it's usually because you have like a pitting inside of the outer race or the inner race, or there's a defect on the actual ball bearing itself. And one of the interesting things to note is the reason why we know of like fault characteristics like a BPFO number is because for the same given bearing, it has the same number of balls, the same inner diameter, the same outer diameter, which means that the faults are going to occur at the same frequency as long as it's running at the same speed. So the actual width spacing is related to the BPFO number, which is going to be the same for the same type of bearing no matter what. So here we can see the spacing up here was basically the same as the spacing down here, which is a good indication that these are the same type of bearing. But if it was the exact same bearing, this frequency should be in the same spot as the big frequency up here. But because it's not, and we actually see two separate scenarios, this would be a pretty good indication that there's actually two bearing faults, because one of them is, if we look at just the centers, let's say this center right here and this center is actually slightly lower than 50,000 CPM, and this one is slightly higher than 50,000 CPM. And so on a bearing, the center frequency is related to what we call the ringing frequency, where the ringing frequency is related to the actual audible tone that you hear when you impact something. So for instance, if you have a tuning fork and you strike it, the tuning fork is designed such that its natural resonant frequency, i.e. the tone that it gives off when it rings, is one that you can hear and is tuned such that it's a specific note so that you can use it to tune your guitar or your piano or something. But the resonant frequency is related to the amount of mass that's at that location. And so here we have two different center frequencies, which would mean that there's likely two different natural frequencies. And the only thing that's going to cause two different natural frequencies is either a different stiffness or a different mass relative to it. So we get the same spacing because they're likely the same type of bearing, which would make sense because if you had a fault on the outboard and a fault on the inboard, when someone went to design that machine, it would cost an extra amount of money to design it with two different types of bearings, i.e. two different shaft diameters or different ball numbers. So most of the time people are just going to design their machine with between the inboard and the outboard having the identical type of bearing. And so that means that the spacing frequency is going to be the same because it's related only to the geometry of the balls relative to the inner race and the outer race and the speed it's going at. But the center frequency, i.e. what it rings at, is going to be related to the relative mass there. And if you just think about it, if we look at what the definition of the equation for the resonant frequency is, i.e. the natural frequency, it's basically related to the stiffness of the system divided by the mass. So if the mass goes up, the resonant frequency shifts down. And if the mass goes down, the resonant frequency shifts up. And so if we're looking here, and we were just looking at this fault right here, if we increase the mass, i.e. if we were just looking at this bearing and it had a fault, and then this bearing had a fault, if they were completely identical scenarios, then the peaks should line up identically, even if they both have faults. But because they're at different locations, that helps indicate that they're different bearings, because the natural frequency, i.e. the center portion, is different, which means one has been shifted slightly due to a weight discrepancy or stiffness relative to the other one. And here we can just think about that logically by saying that the inboard has this big shaft sticking off the end of it. So this side of the motor physically weighs more than this side. I mean, I think most people would agree with me that that part's pretty obvious, is that over here, since you have the part of the shaft hanging off, this side is physically going to weigh more than this side. And again, like I said, when the weight goes up, the natural frequency goes down. So the center frequency of our ringing, i.e. if we have a bearing problem and it comes around every so often and it just hits, it's going to be slightly lower of a ring, what you would be able to hear, than the other one. And so this right here helps indicate that there's two different bearing faults going on. And one of the ways we can confirm that is, again, the center frequency, the big one, is not the same on both, but none of the peaks are, i.e. the big peak here, you can see a leftover result right there, and then this peak right here is right there, and this peak right here matches up with the big one here, and this big peak matches up with this little one there. And another way to look at it is if we go zoom out, and so we go look at the original scale, let's say right there, right? We can hit this demodulate button. So what the demodulation does in DT6 as opposed to other pieces of software is most pieces of software require that you type in some parameters for the demodulation itself to include what low pass filters and what high pass filters you use. But we decided to use what we think is a pretty good fit for most scenarios people are going to deal with based on experience of what size shafts and what size motors people actually use. We have numbers put in there automatically that will fit most machinery people have, as long as it's not enormously large or enormously small. Particularly small, I should say. And basically what demodulation does is it's a feature available in a lot of software, but we've tried to make it a little bit easier by just letting it be a simple click button. But when you click that, what it does is first it high pass filters, which means it gets rid of all the low frequency information and is just going to leave the high stuff. So all it's going to leave you is the information of the signal that's left in the higher frequencies. Then what it does is it rectifies it, which basically takes, if you look at the time waveform, what it literally does is take all the values in the negative and make them positive, which takes the energy out of the negative region and puts 100% of the energy into the positive region. And then the final step it does is it low pass filters it. So when you low pass filter, after you've done the rectification, what you effectively do is take the information out of the high frequency impacts that are related to the bearing faults, and you take the energy out of the high frequency information and put it into a low frequency information form. And so for bearings, what we have is the high frequency information is related to the impact itself, i.e. the physical hitting of, let's say, the ball on the outer race, but the rate at which those occur, i.e. you get a ting and then a ting and then a ting and so on, that is related to the BPFO number, the BPFI number. And when we demodulate that, what we're effectively doing is getting the frequencies associated with the repetition of the higher ones. And so if we go ahead and just click this on, the first thing we notice is that we started off with amplitudes relatively small down here, but when we demodulate it, we magically get higher ones. So if we go ahead and zoom in down there, and again, I'll put it on a scale. We'll go ahead and match the two of them together. If we turn off demodulation, we notice a couple things. That the fundamental speed of our motor is over here at 15 hertz or 900 RPM. I know it because I measured it with a tack. And if we turn on the harmonics, firstly, when we have demodulation on, we get frequencies that were not very large to begin with, i.e. right there and right there. But more importantly, they're not harmonics of our fundamental frequency. And we can do the same thing over here if we put this guy at 15 hertz and we turn on its. Again, we see these peaks that were relatively small before, but after we take the information of the high frequency and convert it to a low frequency form, we see these peaks that get larger amplitudes. And they're not harmonics, so what frequency are they at, you might ask? Well, let's go ahead, turn off the cursors, and we'll just try and jump to this one. And if we look here, let's go ahead and sort by horizontal, because that's the actual frequency. We can jump to any frequency right here that's above a tenth of the way up this vertical scale based on this cursor. So in this case, we have horizontals being the tall ones, and basically this list will populate with every frequency that is above 0.07 Gs in this case in decreasing order. So the first frequency that shows up is just called middle, which puts it in the middle of the screen. But the next one with the number is defaulted to the frequency of the biggest peak. And we can see here, this peak is, 0.69 Gs, 0.8 Gs, or sorry, 0.7 Gs. Relatively large. And it has a frequency of 5520. Now you'll remember that when we had 5520, that was roughly the sideband frequency from earlier. And if we look at this guy, we can also just drag the cursor across till we put it in the right spot. Again, 5520 hertz. And if we turn on harmonics, look at that. We get harmonics of this frequency, so not related to our fundamental and not a harmonic of our fundamental, but this random frequency has its own associated harmonics, but it only occurs when you demodulate it. When you don't demodulate it, it starts off relatively small. And if we leave those harmonics on to see kind of where those other peaks would have been, they're barely even noticeable, but when you demodulate, look how big they get. So that's pretty good indication that there's some energy that are in higher frequencies that are related to a certain repetition impact over time, and that repetition is 5520. And you'll notice that it's basically the same frequency for the outboard as it is for the inboard, which is a pretty good indication that we have a bearing fault with a BPFO number. And if I knew the specific details about this bearing, which I unfortunately don't, we could probably look it up, and this frequency right here, this 5520 CPM, would be more than likely, i.e. as a function, if we do, let's just go ahead and open up a calculator. We do 5520 divided by the 900 RPM of the fundamental, just about. We end up with 6.1, not 6.0. So that means it's not a harmonic, and we can confirm that by the orders. If I put my cursor in the right spot. Hold on a second here. We'll just zoom in right here. And we'll put this on the fundamental speed, which is right there. There we go. And we'll go back. And now we turn on orders. There we go. You can see that it's close to 6, but it's not exactly 6. And if it was a true harmonic, it should be exactly 6. And so what that tells us is that we have this demodulated peak that's not a harmonic of the original speed, but it's within the range of what most BPFO, BPFI numbers are, which is somewhere between just about, let's say, 4 to 8 orders. And we look at it, again, 6 orders, that's just about the right spot. And if we go ahead, and again, we see these spacing impacts of harmonics, that's a pretty good indication that this has a lot of energy because it has its own harmonics. And again, we'll keep in mind this 5520 that's the same in both. And if we go ahead and zoom back out, we don't have the demodulation on, and we look at the sideband spacing again, and we type in exactly that number, 5520. Let's do the same up here. 5520, and then let's zoom in, say right there, and we put this on our highest peak. You can see that it matches exactly, and so that indicates that that peak that we saw down low, that 5520 CPM, is actually the characteristic responsible for creating these sidebands in both the inboard and outboard. But as I said earlier, the center frequency here and the center frequency there aren't the same. So what we've just come up with is the idea that we have two identical bearings, i.e. indicated by a similar, in this case identical, fault frequency, which might be the BPFO or the BPFI frequency, but that the center frequency related to the ringing, which is related to the overall stiffness and mass at that location, are different. Which means these are two different bearings, because if they were the same, bearing, you would expect one of them to be the source. Let's say this was the outboard was the side with the bearing problem. Well, we would expect the vibration here to be large, here to be much smaller, but for the frequencies to line up exactly where they were on this side. But to the contrary, we see similar vibration levels across both of them, and the high peaks here do not line up with the high peaks here, which is a really good indication that there's two different bearing faults going on. Really good indication. So then we go ahead and look at, let's say, the pump side, just for the sake of thoroughness. And one of the things we notice is, let's put these on the same scale. What we have is a large amount of horizontal noise. And bearings, as they become to move into the higher and higher faults, they start to develop higher and higher noise characteristics underneath those peaks. We see peaks that lined up exactly where they did before, so they're bleeding across from the motor side because the motor side has way higher acceleration values than the pump side does for the same given thing, but the peaks themselves are in this similar location and we get a much higher noise discrepancy. So this would be a relative indication that our bearing is not only failing, but the two bearings are close to death because we get an increased noise floor, which is characteristics of bearings later on in life. And that is likely due from the fact that the motor side, if we look at the motor side again, has these large vibrations that are probably a bearing fault on both bearings. So now that we know that we have a bearing fault, or in this case, two bearing faults, what's the next course of action? Well, most people would say, well, fix the bearings because these are clearly about to break, which is true. They're definitely about to break, but that would be only part of the answer. What we're looking for is what's causing the bearings to fail, because they wouldn't necessarily be failing this quickly if there wasn't anything else going on. If there wasn't anything else going on, they should be doing relatively fine, seeing as that when I talked to the guy who this data actually came from, and when I went to his facility to consult and got the data, they had only just replaced these bearings 2 months prior, and this is already where they're at. So that's a pretty good indication that we have bearing faults happening where he just replaced it 2 months ago because they were broken, and now they're already big. There's probably an underlying factor here that's causing this. So now in the next part, we're going to go ahead and try and look at what it is that is causing these bearing faults in the first place, so that after we fix the bearings, we can go ahead and try and fix the original thing causing this to see if we can make our bearings last longer in the long run. Because if all we do is fix bearings, it's going to get very costly, knowing that there's something underlying here causing these characteristics.